So we're back to chapter 9. Last time we were looking at different ways to do calculations to figure out concentrations of solution. This time, what we're starting with is dilution. So we have a solution already made that has some concentration, and that concentration can be molarity, which is moles per liter. It can be mass by volume, which is grams per milliliter. It can be volume by volume. Where you have milliliters over milliliters, or you can have liters over liters. So those are just some of the different ways that you can express a concentration. It's just a reminder. Now what we can do is taking a concentration and a volume of a solution we already have, figure out how to make a solution that is more dilute. And that means it has a concentration that's less than what we started with. So if you've ever taken those juice concentrate things, I don't like them, but they're usually in the freezer section. You take that and then you add in, your water and you mix it. You're diluting what's in that can to make some kind of juice drink. It's the same idea here, only we're talking about chemical substances that you wouldn't exactly want to drink. So a dilution has water added to it. And the volume of your dilution, or the volume of the solution, increases. So if you have a flask and it's got some volume in it, we'll make it yellow. If you dilute that, you're going to have a bigger volume. So that's all that's saying. There's your dilution. Your concentration is going to decrease. But the mass of the solute is the same. So if you think about that orange juice example, it's still the same amount of juice, it's just more water. So the amount of solute is the same. When we're trying to figure out concentrations of initial and diluted solutions, we can think about the number of moles that we have. So the moles of solute are the same in both the initial and the diluted solution. And we can use this equation to figure out what the concentration or the volume is of a new solution. So C is your concentration, V is your volume. If you multiply the concentration that you have by the volume that you have, that gives you the number of moles. Concentration times volume gives you the number of moles. And that's assuming that your C is in moles per liter. And your V is in liters. You can use other kinds of concentration, but we're talking about moles specifically right now. So if you multiply your molarity by your volume, you'll get the number of moles that are in your solution. The number of moles shouldn't change. So the new concentration, or the C2, multiplied by the new volume, your V2, should be the same, and that's how this equation works. If you have other concentration types, like the mass per volume or the volume per volume, which volume per volume is a little bit different, but we'll stick with mass per volume, then you get a percentage like 14%, and then you get a number of milliliters, like 10 milliliters. You can still use this. It's just that you can't exactly use it for mole. And I'll show you some examples later on. This is just another visualization of diluting a solution and what that looks like. So if you were able to look and see individual molecules, you would see that in the dilution, there's more space between the molecules. That means they're further apart. There's more solvent, aka water. So I think it's more helpful to do some problems. So I'll do a problem for you, and then we can pause for questions. So our question is, what is the final concentration when 0.5 liters of a 6 molar HCl solution is diluted to a final volume of 1 liter? There's a lot of information here. What I like to do is write down each of the numbers that I have and what they represent. The first number I came across was 0.50 liters. And that represents a volume of some kind, and it represents V1, or our initial volume. The next number that we came across was 6.0, and that big M is molar, which is moles per liter. This is our C1. It's our initial concentration. And I abbreviate concentration CONC with a period. So this is our initial solution. You have to get the context clues to know which solution the numbers are associated with. Now we say, is diluted to a final volume of 1 liter. That's another volume, but this time it's our V2 because it has to do with our dilution. So this is our diluted volume. We don't have anything in terms of a concentration for our dilution. So that means that's what we're trying to find. And if you look at the question, it says, what is the final concentration? The equation that was on, I think, 2 slides ago, gave us C1V1 is equal to C2V2. So our initial concentration and volume multiplied together should equal the diluted solution concentration times its new volume. In this case, we're trying to solve for our new concentration. So I circle that so I know what I'm solving for. And then I isolate it. So C2, you have to divide by V2 on both sides to get to it. So it's kind of reminiscent of what we were doing with the gas laws, where you have to rearrange an equation. Then you go back to your initial information and fill in all of the numbers. For C1, we have 6 molar. It's our initial concentration. The initial volume was 0.50 liters. Our diluted volume, our V2, is 1 liter. Our units cancel so that our answer should be molar. That's good because we're looking for a concentration. 6 times 0.5 gives you 3. and 3 divided by 1 is 3. So that means our new solution is now 3 molar. Questions, comments, concerns? If you're good, you can say you're good. If you're not, you can say hold up. Okay. We got a couple of good, many more good. All right. So then we're going to move on. I'm going to let you guys do an example. So what volume of a 2% mass by volume HCl solution can be prepared by diluting 25 milliliters of 14% HCl solution? So this is, don't get confused by the different, oh, now it says 2% mass by volume. Don't worry about that. You're still using the same C1 V1 equals C2 V2. So my first question to you is, what variable are we trying to solve for? What is the question asking? Are we looking for C1, V1, C2, or V2? You can write it in the chat. Yeah, we're looking for V2. It says what volume of this concentration solution can be prepared by diluting. So that tells us our volume is the diluted volume that we're looking for, which is always V2. That means we have to know everything else. What's our C1? What's our initial concentration? Ah, you got tricked. The 2%, yeah, that 2% is lower than the 14%. And your dilution is always going to be lower. So your C1 is 14.0%. And the C2 is 2.00%. There's only one other number left, and that's 25 milliliters. So that's got to be our initial volume. Using this information and knowing that you're solving for V2, try to solve for V2 and see what you get. You can put your answer in the chat once you get it. What are the units on that? Naked numbers are no good. Remember, it's a volume. It should be milliliters because that's what the other volume is in. Yeah. So for this one, I'll write it out just so that it's with the notes. We're looking for V2. So when you isolate, you should get that as your equation. And when you solve, 14% is your C1, V1 is 25 milliliters, C2 is 2%, and you should get 175 milliliters. Always have your unit. Questions on that? Raise your hand if you want to move on from doing dilutions, because we can move on and yeah. Okay. So doing dilutions is pretty simple. All right, you can lower your hand. There's another one in here if you want to try it on your own, and I will give you the answer. So let's see. Your molarity, which is your C2, should be 0.2 molar. So if you want to do this on your own time, multiply it with the percent. Think about it like it's just a number. I did the percent there just so that I kept track of when I'm doing my units what cancels. So use the percent. It's a good question. You're welcome. So there's the answer for that learning check question if you want to go back and do it. Right. Now we're going to move to chapter 11. We talked about dilutions, which means that we're adding water to a solution and decreasing the concentration. Now we're going to talk about water itself. So water is a great solvent. It's known as the universal solvent. It's polar, got hydrogen bonding, lots of very special things about water that makes it so precious to us. Water can react with itself, and you can create hydrogen ions and hydroxide ions. So you see this H3O+. That's the same thing as H+. It's just that you don't have a single hydrogen hanging out. What you really have is an oxygen with 3 hydrogens, and it has a positive charge, just like what's depicted here for this water molecule. Okay. H3O+ has an extra hydrogen, which makes it an acid. OH-, it lost a hydrogen. It's now negative and looking to pick up another hydrogen. That makes it a base. So we're going to talk about this equilibrium reaction where water is creating an acid and a base. We're going to introduce a new term called amphoteric. That means that it can act as an acid or a base. So it can donate or receive a hydrogen. That's what amphoteric means. It can do both. So you can transfer a hydrogen from one water molecule to another, and you reach some kind of equilibrium. What you'll also see associated with this is the term conjugate acid and conjugate base. That just means that something is turned into an acid or turned into a base. So this water molecule here that I just underlined, it has lost a hydrogen. And now it's OH-. That means it's an acid. It donated the hydrogen. The conjugate base is what's formed from donating the acid. So these always come in pairs. After an acid donates its hydrogen, it becomes the conjugate base. The same is true for the base. The base will gain a hydrogen, and it'll go from being a base to being a conjugate acid, where there's this new hydrogen that is added to it. So those are conjugate acid-base pairs. Questions about that? There aren't going to really be questions about what is the conjugate acid and what is the conjugate base necessarily, but understanding how it works in terms of something lost a hydrogen, and that means that it started as an acid and now it's become a base. Understanding that is key. So are there any questions about that? If there are, ask it. If not, you can say you're good. All right. Much appreciated. So for that reaction, we can actually write a dissociation constant and equation. We did that with acids before, where we're making the H plus and some kind of conjugate base. It's the same thing for water. For pure water, the concentration of this is called the hydronium ion. I'll also just call it H plus for short. So the concentration of H plus and OH minus at 25 degrees Celsius is 1 times 10 to the minus 7 molar. So water doesn't make a whole lot of conjugate acid and base. This isn't a reaction that is fruitful, okay? But it does happen a little bit. And if you multiply those two together, you get the Kw. And that is 1 times 10 to the minus 14. So this gives you a rate constant. We're going to use this equation and we're going to be able to solve for concentration of H plus and OH minus. So this is the equation we're going to be using. And this slide just kind of describes what I've said already in words at the top. But at the bottom is what I really want you to focus on. And I'm going to rewrite this kind of using symbols. We're looking at the different concentrations of these ions. When H plus and OH minus are equal, your solution is neutral. If you have more H plus than OH minus, then you're going to have an acid. Okay? That's what an acid is. It can donate hydrogens. So if you have a lot more hydrogens to donate, that means you're acidic. If, however, you have less H plus than OH minus, you're basic. So you need to remember those. We're going to be talking about substances that are neutral, acidic, and basic. This is one definition of how we can say something is neutral, acidic, or basic, and we're going to be adding on to that. So my recommendation for this part is to, when you're going back through your notes, when you're doing homework, make a little chart that describes neutral, acidic, and basic, and the different ways that you can define those things. So this is the first way when we're looking at the concentration of H plus and OH minus. Now, like I said, we can use this equation, the Kw is equal to the concentration of hydrogen plus times the concentration of OH minus. If we know one of the concentrations, then we can figure out the other. So you're going to be using these two equations to either figure out the hydroxide or the hydronium. The next few slides is going to be more of a visualization of the different concentrations of the hydronium and the OH minus, the hydroxide. So water is neutral. That means that both of those ions, we've got the same. So you can see these two bars are the same. Let me get my little laser pointer. So these two levels are the same. If you have an acid and you're adding that to pure water, your amount of hydronium, that H plus, is going to increase because you're adding an acid. An acid donates hydrogen ions. So you're going to have more hydrogen ions, which means you're going to have less hydroxide. So that means you're going to have an acidic solution. So the bar is much higher for the H plus than the OH minus. And finally, if you add a base to pure water, you're going to increase your hydroxide and you're going to decrease your H plus. So that's, again, another way to visualize it. If just the plain old, greater than, equal signs, if those don't make sense to you, these bar graphs will help you visualize what that looks like. Any questions, or are you good? All right. I appreciate it. When we're doing a lot of me talking, it's easy to get lost. My voice is melodic, I understand. And that YouTube video or movie that you have on in the background because you're using your Philo subscription for 7 days for free, very appealing. So I appreciate the feedback. So this slide is just a summary of the three smaller slides that I went through. And again, if the bar graphs make more sense to you, then you should put that into your notebook. This table gives examples of neutral, acidic, and basic solutions and their different hydroxide and hydrogen plus ion concentrations. And it shows that your constant concentration, your 1 times 10 to the minus 14, when you multiply those two together, that's always what you get. So let's solve a problem. It's what it's all about, right? What is the H plus concentration of a solution if the OH minus concentration is 5 times 10 to the minus 8 molar? The first thing we have to do is figure out what the heck we're solving for. It says, what is the hydronium concentration? So that means we're solving for the hydronium. So I circle that. I always circle whatever variable it is that I'm trying to solve for. And our known is that our concentration of OH minus is 5 times 10 to the minus 8 molar. We need to rearrange this. Since we're solving for the hydronium, that means we need to divide by the hydroxide concentration on both sides. So we're going to get 1.0 times 10 to the minus 14. And there's no units there. The units are dropped for the kW. But just remember that the concentrations of the different ions is always in molar. molarity. So you take that Kw and divide it by the hydroxide concentration, and that should give you your hydronium concentration. When you fill that in, that's what you should get, and you just put it into your calculator. So give it a shot, put it into your calculator. Oftentimes with these problems, it's not an issue of understanding the question, it's an issue of putting it into your calculator properly. So put it in the chat what you get once you have a number. Don't forget your units. Yeah. So you should get 2.0 times 10 to the minus 7 molar as your concentration for the hydronium ion. If you're having issues with putting in exponents in your calculator, if you just need a refresher, that's fine. You can just email me or stop on by office hours tomorrow or Thursday. But we're gonna be doing some calculator calisthenics for this one to brush off the cobwebs of how to do logs and 10 to the, doing exponents and all sorts of stuff. All right. So now it's your turn. I want you to do this problem. If lemon juice has a hydronium concentration of 2 times 10 to the minus 3 molar, what is the OH minus concentration of the solution? Give that a shot, and you can put your answer in the chat box. If you're a little bit lost, I'll help you out. We're solving for the hydroxide concentration. That equation should get you to the answer. Does your calculator, some calculators will put the exponent in the corner. So if there's a number in the corner of your calculator display, Kennedy, that would be your exponent. So I got C. Yeah. Oh, okay, yeah. That is not it. So make sure that you're dividing. And make sure that you're dividing, Kennedy. But that's it in terms of using the concentrations of hydronium and hydroxide and the KW. All right. Well, Kennedy, if you have issues with your calculator, you can send me an email. You can take a picture of your calculator and what it's saying, and we might be able to figure it out. And that goes for anybody. If you're having issues with how to use your calculator, let me know. You're welcome. The final section that we're going to cover is the pH scale. And this is related to what we're doing because the pH scale tells you about the hydronium concentration. So let's look at that a little more closely. The pH scale is another way to classify whether or not a solution is acidic, neutral, or basic. The value that you're usually going to see for pH is 0 to 14, where 0 is super acidic, 7 is neutral, and 14 is basic. So between 0 and 7, you're going to have an acidic solution. If it's between 7 and 14, you're going to be basic. And down here, that's what we just said for the pH. And this other part where we're looking at the hydronium concentration, that is another way to say the same thing. So you can add both of these to your chart that you make to describe acidic, neutral, and basic solutions. If you're acidic, then your hydronium concentration is going to be greater than 1.0 times 10 to the minus 7. So that means it could be 1 times 10 to the minus 5, something like that, okay? So greater than means that this exponent, that 7 is going to be small. It's going to be a 5 or a 2 or something like that, minus. For a neutral solution, the concentration of hydronium is going to be exactly 1.0 times 10 to the minus 7. And for a basic solution, you're going to be looking for a hydronium concentration that is less than 1.0 times 10 to the minus 7. So an example of that would be something that's 1.0 times 10 to the minus 10, okay? That is going to be smaller than 1.0 times 10 to the minus 7. So just remember how exponents work, especially negative exponents. That's not something that we use a whole lot, so refresh yourself on that if the math skills are a little bit, cobweb-like. There's lots of ways to measure pH. You can use a pH meter, like in A, where you have a probe that you stick into your solution, and it will tell you, flat out, that's your pH. You can also use pH paper or an indicator, and both of these things work by color change. Notice that on this packaging, there's different colors associated with each pH. So pH, the more acidic you are, the more kind of magenta pink you are. And then as you approach neutral, it's more of an orange. Green is neutral, 7. and then you go from that green to kind of a darkish blue purple. Those are a little bit more difficult to interpret because it's not an exact number. But that's just some of the ways you can determine what your pH is. This is a pH scale that gives you kind of a baseline for what's acidic and what's basic, just an everyday thing. So lemon juice, vinegar, the soda that you might be sipping on, those things are acidic. Citrus is also acidic. Let me switch to my pointer. So all of these things are acidic. Milk is almost neutral. Pure water is neutral. The water that comes out of your faucet, or if you're using a Brita filter or anything like that, that's going to be about 7.2, and that's close to neutral but not exact. Your blood is a little bit on the basic side. The detergents that you might use to wash your clothes are definitely basic. Ammonia, bleach, cleaning agents like that, they're pretty basic. So those are quite caustic. So anything that's very acidic or very basic, you need to be careful, as you can injure your skin and certainly your eyes. So like I said, you're going to need to be able to identify solutions as acidic, basic, or neutral. Let's try A through C. So you can put it into the chat box. Identify each of these, A, B, and C, as acidic, basic, or neutral. You can just put it in order. A is what, B is what, and C is what. Okay, we're calling A acidic. I agree with that. Oh, it's all right. B we're calling basic. And C, acidic. Good. So you can do the rest of these if you would like on your own time, but I think that you get the concept. You're going to be able to answer. You're going to need to be able to answer these kinds of questions for your homework and for the exam. So that table that has the different ways you can classify something as acidic, basic, or neutral will really come in handy. Let me know if you're good or if you have questions. So you can say I'm good, or you can ask a question before we move on. Cool. So it wouldn't be complete without some math, but I promise it's not that bad. We got to talk about how to calculate the pH of a solution. The pH scale is a logarithmic scale, which means it doesn't go up linearly. It's not just 1, 2, 3, 4 like you're counting in order. The concentrations increase in a particular way that's called a logarithmic scale when you're going from pH 1 to 2 to 3. To define the pH, we're going to define that as the negative log base 10 of the concentration of hydronium. Now what I want you to do is take a second and figure out on your calculator where your log button is. Some calculators just have a log button, but if you have a TI-89, it's not going to be that simple. With the 89, you actually have to go into the catalog and search for log as a function. There isn't just a log button. So make sure you know where the log button is. It might be written as log with a 10 after it, or just a log like that. That implies base 10. Make sure you know where that is. If you can't figure it out, you can always Google the calculator that you have, and it'll tell you how to figure it out. Google is great. When you're calculating the pH, what you need is the concentration of hydronium. Once you have that, you place that into the brackets. So you put into your calculator the negative button and then log, and then put your number in parentheses. So you should get a positive number. Let's do an example. Oh, we're not at examples yet. Significant figures. Sig Figs for pH is a little bit different. So here in our concentration, we have 1.0 times 10 to the minus 2. That means that we have 2 Sig Figs. When you report your answer, you need to have 2 decimal places. The number of Sig Figs in your concentration represents the number of decimal places that you have to have after the decimal. It's a little bit strange, but that's the rule. So when you're increasing your pH unit by 1, you're increasing your concentration by 10. And that's what the log scale means. So to go from a pH of 2 to a pH of 3, you're changing your exponent from -2 to -3. And that's a 10-fold difference. Now we can do a question. Aspirin, which I'm sure everybody is familiar with, is acetylsalicylic acid. It's a non-steroidal anti-inflammatory drug. So if ever you see the NSAID, that's what that stands for, non-steroidal anti-inflammatory drug. You use it to alleviate pain, fever, toothache, all sorts of things. If you have a solution of aspirin and it has this concentration, 1.7 times 10 to the minus 3 molar for its hydronium concentration, what is the pH of the solution? I don't know if CVS is getting a kickback for that, but when I was looking through this, I was like, man, that branding is just out there. I wish I'd get some dollars for that. Anyway, so here's that question without all the jazz, okay? If a solution of aspirin has this concentration for hydronium, what is the pH of the solution? pH is equal to negative log of your hydronium concentration. So in this case, it's negative log, and then you put in the 1.7 times 10 to the minus 3. If you found the log button and figured out how to use it, give it a shot and let me know what you get. If you haven't found your log button, you can let me know that too. Yeah, so D, you got it. It's 2.77. Remember that there's 2 sig figs in our concentration, so that means that we need to have 2 decimal places. So sig figs for pH is a little funky. Now let's do a double check. I always like to include some kind of a mental math check to make sure that our answer makes sense. We have a pH, or we have a hydronium concentration of 1.7 times 10 to the minus third. Should that be acidic or basic? We'll let some other folks chime in, see where everybody's at. It should be acidic. Then we look at our answer, 2.77. Is that acidic or basic? It's acidic, right? If you're unsure of your calculator skills, use that mental check. Look at the hydronium concentration and say, okay, am I expecting this to be acidic or basic? Then when you do your math, see if it lines up. So always do that as a check. It will help you. It will save you points on the exam too. Here's another example. We don't have to do this example. I think that those of you that are participating understand. So I guess raise your hand if you want to move past this example and finish up with the last bit of information I need to give you. Okay, I'm all for it. I'll just give you the answer. The pH for that one should be 4.40 with the correct sig figs. The final thing we have to do is calculate the hydronium concentration from a given pH. So for that, we're going to do the opposite in terms of function. If log base 10 gets us to the pH, the opposite of that is doing 10 to the minus pH. Some calculators have a 10x key like that. Others, you just have to enter in 10 and then the caret and then your negative pH. So make sure that you figure out which flavor of calculator you have so that you can do this calculation. So this is going to be our final example. You have to determine the concentration of hydronium for a solution that has a pH of 3.42. This is our equation. What you're putting into your calculator is that expression right there. So however you have to do it in your calculator, Figure it out and let me know what you get. Yep. And don't forget, this is a concentration, so it's molar. For a question like this, you will very likely need to write it in scientific notation. The way that you can double check your answer is by using the equation that we just did for pH. pH is equal to the negative log of your hydronium concentration. So if you do that using your 3.8 times 10 to the minus 4, you should get 3.42, or at least something close to it. I think it's 3.420 something 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 that you get for the pH. So that's a way to check your answer if you're unsure about whether or not you did the calculation right on your calculator. You can always double check with the pH calculation. Any questions about that? Okay. That's all that we have for this class. That is